We're seeing AI really move beyond just single standalone systems these days. Now we're talking about multiple AI agents actually collaborating these multi-agent systems, right? They're tackling really complex stuff.
Yeah, it's a big shift.
It's exciting, definitely. But I imagine it also opens up, well, a whole new can of security worms.
Absolutely. I mean, think about it. Instead of just securing like one door,
Right.
you're suddenly securing this whole network of interconnected rooms. And, each room has its own potential weak spots, its own ways an attacker might get in.
So the complexity just ramps up.
It multiplies, yeah. And with that, the potential for things to go wrong, maybe in ways you didn't even expect.
Okay, so for this deep dive, we're really going to plunge into the specific security threats that pop up in these multi-agent systems.
Sounds good.
And we've got a pretty interesting guide to help us navigate this.
Yeah.
It's from the OWASP Gen AI Security Project. It's called the OWASP Gen AI Security Project. It's called the Multi-Agentic System Threat Modeling Guide V1.0. Just came out last year, April 2025.
Oh, right. I've seen that one.
Yeah, and it's openly available, too, under a Creative Commons license, which is great.
That guide is, it's vital, really, because it gives us a structured way to look at the security landscape of these pretty intricate systems.
So our mission today is basically to understand the unique challenges these systems bring.
Exactly. And specifically how this framework they introduced called MAESTRO can help us, spot those potential weaknesses.
Maestro.
Yeah.
Okay, that sounds intriguing. What exactly is it?
So MAESTRO stands for Multi-Agent Environment Security, Threat, Risk, and Outcome. It's essentially a blueprint. Like an architectural way of thinking about how you find threats, specifically in multi-agent systems. It looks at the system in layers, kind of like peeling an onion,
Right, layer by layer.
To understand where vulnerabilities might be hiding. And it works alongside the OWASP Agentic Security Initiative, the ASI Threat Taxonomy.
Oh, okay, so it complements that.
Yeah, it offers a more detailed kind of layer-by-layer approach to the risk analysis. It identifies 7 key architectural layers. And this is crucial. It also looks at the risks that can emerge from the interactions between those layers.
Okay, 7 layers plus these in-between risks. So it's not just the individual pieces, but how they talk to each other.
Precisely. Think about a building, right? Its strength isn't just the bricks.
It's the mortar, too.
Exactly, how they're connected. So this guide uses MAESTRO to really dig into these multi-agent scenarios. And it expands on the existing ASI taxonomy, too.
How so?
By highlighting threats that are more specific to these multi-agent setups. Things like, what if one AI model in the system becomes unstable? Or what if a tool an agent uses gets compromised?
Or even if the agents themselves start messing with each other.
Yeah, like interfering in harmful ways. It covers that, too.
That makes sense. So it's taking a broader view beyond just the single AI.
Yeah. And
the guide uses real-world examples, right?
Absolutely, and that's where it gets really practical, I think. We get these detailed threat models for an AI agent that handles expense reports, an entire AI operating system called ELIZA OS,
right,
and the Anthropic MCP protocol, which is basically a way for AI to connect to external data and tools.
And it also emphasizes these agentic factors. What are those?
Yeah, those are things inherent to AI agents, like the fact that they might not always make the exact same decision every time, non-determinism.
Okay.
Or how much independence they have, their autonomy, how we verify agent identity, like who is who in this digital crowd, and the complexities of how they communicate.
Lots to consider.
And finally, it gives some really concrete advice on, how to actually build and deploy more secure multi-agent systems.
Sounds like essential reading if you're working in this space.
Yeah.
And it builds on other OWASP work, I gather.
Yes, it's definitely designed to work hand in hand with OWASP's Agentic AI Threats and Mitigations document. That one lays out the core ASI threat categories.
Okay.
And it also recommends keeping the OWASP top 10 for LLM applications in mind because, these large language models are often the brains behind these agents, right?
Makes sense. So before we get into MAESTRO's layers, let's just nail down what we actually mean by multi-agent systems. What are they, fundamentally?
Okay, so at its heart, a multi-agent system, or MAS, is basically a collection of autonomous agents. Think of them as individual AI entities.
Right.
And they operate in some kind of shared environment to achieve goals. These goals could be their own individual objectives, or maybe something they're all working on together.
And these agents, are they all the same?
Not necessarily. They can be very similar, homogeneous, or quite different with different skills, heterogeneous. They might work step by step or all at the same time in parallel, or maybe even in a hierarchy.
Right.
The key thing is they communicate and coordinate somehow. Sometimes they cooperate. Sometimes they might even compete for resources or tasks.
Okay, so a team of AI individuals working together or sometimes competing in the same digital space. What are some of the key characteristics that define these systems?
Well, the guide lists quite a few. There's distributed autonomy. Each agent makes its own decisions but contributes overall.
Right.
Then interagent communication, obviously they need to talk. Collaboration and competition, like we just said. Then there's emergent behavioral. This one's really interesting. It's when complex system-level actions arise just from the simple interactions of individual agents.
In ways you didn't necessarily program.
Exactly. Often unexpected ways. They also tend to offer scalability and adaptability. You can often add or remove agents fairly easily.
Okay.
The control can be centralized, hierarchical, or totally decentralized. You've got task distribution. Different agents handle different parts of a job.
Makes sense.
Individual agents can have their own memory and learning abilities. They can be heterogeneous, as we mentioned, different skills. Yeah. You might see self-organizing behavior where the system adapts its structure on the fly. Yeah. They interact with the outside world agent communication. Crucially, agents are independent. They could even be part of multiple systems. And of course, direct agent-to-agent communication.
That last one, agent-to-agent communication, feels like it could be a real hotspot for security issues. Are there any standard ways these agents talk?
It's definitely an evolving area, but the guide does mention Google's agent-to-agent protocol A2A as a promising standard. Okay. The idea is to create a kind of common language and set of rules so agents can figure out what other agents can do and then communicate effectively.
That's good. Standardization usually helps with security, doesn't it?
It often does, yeah.
Now let's pivot to the security challenges. What are the unique problems that pop up because we're dealing with multiple interacting agents?
This is really where the landscape shifts. The guide points out several key limitations, security-wise. First, the attack surface just explodes.
Right, more agents, more doors.
Exactly. You're not just looking at one AI. You have to consider vulnerabilities in every single agent, how they communicate, the shared environment.
Wow.
Trust becomes a huge issue, especially when agents are meant to collaborate. How do you know an agent is who it says it is? What if it's been fed bad data or even has malicious code inside? The coordination mechanisms themselves can fail, or worse, be attacked. Imagine trying to disrupt how they work together.
Chaos.
Pretty much. Then there's explainability and auditability. Trying to trace a decision back through this web of interacting agents, it can be incredibly difficult.
Yeah, I can see that.
We also worry about traditional threats like man-in-the-middle attacks on their communications, but maybe with more complex ways to pull it off.
Okay.
And accountability can be murky. It's not like dealing with a human employee. Finally, just managing identities and access permissions across potentially tons of agents gets really complicated really fast. Identity sprawl, they call it.
It definitely sounds like a recipe for security headaches.
Yeah.
Where are we actually seeing these multi-agent systems being used right now? Give us some examples.
Oh, they're popping up across many different industries. Think about distributed robotics, like in warehouses or for search and rescue.
Okay.
Optimizing really complex supply chains, managing traffic and energy grids in smart cities,
right.
Assisting doctors with diagnosis or patient monitoring in collaborative healthcare settings, enhancing customer service or sales with teams of coordinated agents. And even within the software development lifecycle itself, you might have different agents handling different stages like coding, testing, deployment.
It really shows how widespread these security concerns could become. Now, the guide gives a sort of quick overview of some initial threats in MAS. What are the top-level worries they mentioned first?
Yeah, that initial overview flags things like insecure communication between the agents, the potential for a really wide impact if just one agent gets compromised. They call that the blast radius. Identity spoofing, where attackers pretend to be legitimate agents. Prompt injection attacks, especially if agents use large language models. Risks from external dependency services they rely on.
Okay.
The fact that attacks can just be harder to spot in these complex setups, decreased visibility, and the possibility of agent collusion, where malicious agents actually work together. But as the guide itself points out, Maestro gives us a much deeper, more structured way to analyze all these risks.
Okay, so let's dive into the Maestro framework itself then. What's its core mission? Why was it developed?
The main goal of Maestro is really to systematically map out those security threats that are specific or unique to multi-agent systems.
Right, the ones that arise because there are multiple agents.
Exactly. And it does this by looking at the different layers of the system's architecture. Everything from the foundation AI models themselves all the way up to the broader ecosystem, agents, tools, humans interacting.
Okay.
And crucially, it also focuses on those threats that emerge from the interplay between these different layers.
You mentioned 7 layers earlier. Can we walk through what each one covers?
Sure. So layer 1 is the foundation model. This is all about the core AI models powering the agents. Their integrity, alignment, making sure they behave as intended, and the risks of things like model poisoning or manipulation.
Okay, the core AI.
Layer 2 is data operations. This looks at how data is managed and used. Think vector stores for RAG, prompt management, securing the data retrieval process itself.
Got it. Data handling.
Layer 3 is agent frameworks. This focuses on the agent's internal logic, their execution flow, how their workflows are structured, and the limits of their autonomy.
The agent's brain and rules.
Kind of, yeah. Then layer 4, deployment infrastructure. This is the nuts and bolts where the system runs. Server security, containers, orchestration tools, network security.
The physical or virtual home.
Right. Layer 5 is evaluation and observability. How do we watch these systems? How do we monitor them, detect anomalies, log what they do? Do we need humans in the loop?
Monitoring and oversight.
Exactly. Layer 6 is security and compliance. This one cuts across the others, really. It's about access controls, enforcing policies, making sure everything adheres to regulations.
Rules and provisions.
And finally, layer 7 is the agent ecosystem. This considers how the agents interact with the outside world, humans, external tools, other agents, maybe in different systems.
The neighborhood they live in.
Good analogy. And like we said, there's that unofficial 8th category, cross-layer emergent behaviors. The unexpected stuff that happens when layers interact.
Okay, that's a very comprehensive breakdown. How does MAESTRO then relate back to that ASI threat taxonomy we mentioned at the start?
Yeah, the guide provides a pretty clear mapping. It shows how the MAESTRO layers align with specific threats from the ASI framework.
Can you give an example?
Sure. The foundation model layer in MAESTRO layer 1 that clearly connects to ASI threats like, say, T7, memory poisoning, if the model retains information, or T1, evasion, like causing misaligned or deceptive behavior. Data operations layer 2 maps to things like T7 again, manipulating memory or data stores, and also T12, agent communication poisoning.
Okay.
Agent frameworks, layer 3, that relates to ASI threats like T2, tool misuse, or T6, goal breaking, where attackers mess with the agent's objectives, or even T11, cascading hallucinations if one agent's error affects others.
So each MAESTRO layer maps to relevant ASI threats.
Pretty much, yeah.
Yeah.
It shows how those known agentic threats manifest at different architectural levels.
Okay, so it builds on what we already knew, but you also said MAESTRO goes beyond ASI. How does it give us a more complete picture?
Exactly. Yeah. MAESTRO is designed to be, well, more versatile and maybe more forward-looking. It helps us uncover potentially new types of threats that might not be explicitly listed in the current ASI framework. It also lets us paint more detailed, more complex scenarios of how attacks could actually play out in a multi-agent context. And importantly, it helps us consider non-agentic threats to traditional cybersecurity risks that could still have a huge impact on the agentic system.
Right, because the agents don't exist in a vacuum.
Precisely.
Can you give us some specific examples of these sort of newer or extended threats that MAESTRO helps highlight at each layer?
Yeah, definitely. So at layer 1, the foundation model layer, MAESTRO brings up collaborative model poisoning. Imagine multiple agents are jointly training a shared model, right? A malicious agent could sneak in subtly poisoned data, corrupting that shared model for everyone else in a way that's really hard to trace back.
Wow, okay.
Layer 2, data operations. Distributed data poisoning. Instead of hitting one data source, an attacker targets multiple data sources used by different agents across the system. Makes contamination much harder to spot and clean up. Layer 3, agent frameworks. MAESTRO identifies negotiation hijacking. An attacker manipulates the communication protocols the agents use when they're, say, negotiating for resources or dividing up tasks, skewing the outcome.
Influencing their deal.
Exactly. Layer 4, deployment infrastructure. The risk of distributed denial of service, DDoS attacks, but specifically targeting multiple agents at once to try and overwhelm the whole system.
Okay.
Layer 5, evaluation and observability. This is subtle. Distributed performance degradation masking. An attacker slowly degrades the performance of several agents, while also manipulating the monitoring metrics to hide the fact that anything's wrong.
Sneaky.
Very. Layer 6, security and compliance. Data privacy violations and inter-agent interactions. Sensitive info might get unintentionally shared or leaked between agents just as part of their normal chatter if controls aren't tight.
Right.
And layer 7, agent ecosystem, the threat of malicious agent diffusion. A rogue agent gets in, exploits trust relationships with other agents, and rapidly spreads itself or its influence through the system.
Like a virus in the agent network.
Kinda, yeah.
These are definitely specific and concerning threats, really arising directly from having these interacting AIs. Now, let's talk more about those cross-layer threats. You said they sound particularly insidious.
They really are, because these are the threats that emerge from that complex interplay between the different architectural layers. They often involve emergent behaviors, and Maestro is really good at bringing these to light.
So what are some examples?
Well, you could have cascading trust failures. An attacker compromises one, maybe less protected, agent.
Okay.
Then they leverage that compromised agent's trust to gain access to more critical agents, maybe in different layers. It creates this chain reaction across the system.
One weak link breaks the chain.
Exactly. Or think about system-wide bias amplification. Even small biases in individual agents' data or programming can get magnified as they collaborate and share info, leading to significant, maybe harmful biases at the overall system level, even if that wasn't intended.
Right. The whole becomes more biased than the parts.
Potentially, yeah. Another one is systemic resource starvation. An attacker could exploit dependencies between agents across different layers to strategically drain resources, compute power, memory, network bandwidth, effectively grinding the whole system to a halt.
Wow. These sound like they could cause really widespread damage. Are there more examples of these cross-layer threats Maestro helps us find?
Oh yes, quite a few. Maestro also flags things like cross-agent feedback loop manipulations. An attacker subtly messes with the feedback agents give each other during learning processes, causing the system to gradually learn harmful or undesirable behaviors. Then there's the risk of an inter-agent data leakage cascade. Sensitive data leaks from one compromised agent, then hops to another through normal communication channels, potentially reaching places it should never go.
Data dominoes.
Sort of. Misconfigured inter-agent monitoring. If you're not watching the right interactions between layers, malicious activity could just slip through unnoticed. We also have cross-layer memory poisoning, where attacks target agent memory in ways that span different architectural layers. Tool misuse is a big one. One agent gets permission for a tool, but then delegates its use to another compromised agent that shouldn't have that access, possibly across layers.
Exploiting delegation.
Right. Similar idea with privilege compromise. A weakness in one layer, say infrastructure, helps an attacker escalate privileges in another layer, like the agent framework.
Okay.
Resource overload achieved through coordinated attacks involving multiple agents across layers. Hallucination attacks getting amplified when agents in different layers uncritically trust fabricated information from each other. Agent communication poisoning, injecting false info into communication streams that cross layer boundaries. Temporal manipulation, trying to desync agents operating at different layers to cause errors. Learning model poisoning, where deceptive data is injected via interactions spanning multiple layers. Identity spoofing at a system level, maybe controlling agents across layers to appear as a legitimate group. Planning and reflection exploitation, corrupting the autonomous decision-making that might involve components from multiple layers.
Okay, still going.
Just one more really concerning one. Excessive agency or permission bypass via chained agents. This is where an attacker cleverly chains together the legitimate permissions of multiple trusted agents across different layers to achieve an action that no single agent was ever authorized to perform on its own.
Combining powers for evil.
Basically, yes. It's exploiting the distributed nature of permissions.
That is a truly sobering list. It really highlights this intricate web of potential vulnerabilities. Now, the guide also mentions using Maestro with MITRE Atlas. How do those fit together?
That's a great point. So while ASI, and by extension Maestro, really zoom in on those threats unique to agentic systems, we can't ignore the broader cybersecurity and AI security landscape. That's where MITRE comes in. MITRE 18CK gives us that huge catalog of general adversary tactics and techniques. And MITRE Atlas extends that specifically into the AML domain, covering things like data poisoning, model evasion, adversarial ML.
Okay.
Maestro complements these by providing that structured, layered way to evaluate AML systems, including multi-agent ones, against specific threat scenarios, including those unique agentic ones.
So you use them together?
Ideally, yes.
Mm-hmm.
By using ASI, Maestro, maybe other OWASP resources like the LLM Top 10, alongside MITRE ATT&CK and Atlas, you can build much more robust, comprehensive threat models. You cover the whole spectrum.
Okay.
Maestro helps you think through how these agentic threats might actually play out in a real systems architecture, and you can often map the findings back to specific ATT&CK or ATCAS techniques. It makes your defense planning more informed, more proactive.
Got it. It's about a multifaceted approach for these multifaceted systems. Now, the guide gives us some really valuable deep dives into specific use cases. Let's start with the first one, the RPA expense reimbursement agent. What's that scenario about?
Okay, so this use case looks at an AI agent designed to automate expense reimbursements for employees using robotic process automation, or RPA.
Right, automatic paperwork.
Exactly. The agent's job is to pull key info from expense claims, receipts, forms, etc. Then it needs to check these claims against company policy using retrieval augmented generation, RG.
Using a knowledge base of policies.
Yeah, typically a vector database of policy documents. And then if a claim is approved, the agent initiates the payment process.
Okay, pretty standard RPA task. What were some of the initial baseline threats they spotted, just using the core ASI taxonomy?
So just with the basic ASI list, they identified potential risks like T7, memory poisoning an attacker slowly manipulating the agent's understanding of what's an acceptable expense. T2, tool misuse via prompt injection, tricking the agent into doing something unintended, like exporting sensitive employee data or sending unauthorized emails.
Right.
T3, privilege compromise, gaining unauthorized access to the financial systems the agent uses for payments. T6, intent breaking, messing with the agent's core goal of correctly processing expenses. T1, evasion leading to misaligned behavior. Maybe the agent prioritizes speed over doing proper security checks. T8, repudiation attackers manipulating logs to cover their tracks.
What brain tracks?
T10, denial of service on human reviewers, overwhelming human approvers with lots of bogus requests. T12, agent communication poisoning if this agent talks to others. And T13, introducing unauthorized rogue agents into the workflow.
So a decent starting list of worries. Now, how does applying the MAESTRO framework help us go deeper into the risks for this specific RPA agent?
Right, so the guide then meticulously maps the RPA agent's components onto the 7 MAESTRO layers.
Okay, let's see that.
Layer 1 foundation model. That would be the LLM used for understanding the text on receipts and reasoning about policies.
Makes sense.
Layer 2, data operations. This is the RIG system, including that vector database holding the company expense policies.
A knowledge base.
Right. Layer 3, agent framework. The RPA software itself, the defined workflow logic for processing claims, any tools it uses.
The automation engine.
Layer 4, deployment infrastructure. The servers, cloud or on-prem, network connections, source accounts the agent runs under.
Where it lives.
Layer 5, evaluation and observability. Logging mechanisms, any anomaly detection systems, maybe a human-in-the-loop review step.
How we watch it.
Layer 6, security and compliance. The company's access control policies, the engine enforcing them, and the actual expense regulations themselves.
The rules it follows.
And Layer 7, agent ecosystem. How this RPA agent interacts with humans, employees submitting claims, other internal systems like HR or finance, maybe external services.
It's neighbors.
Yeah.
Okay, a clear architectural breakdown. Now, what extended threats does MAESTRO help uncover at each of these layers for this specific RPA agent? Things beyond the basic ASI list.
Okay, this is where MAESTRO adds value. Layer 1 foundation model, T16 model inconsistency leading to variable approvals. Because LLMs can be non-deterministic, right?
Right, gives slightly different answers sometimes.
Exactly. So the same expense claim submitted twice might get approved once and rejected the next time. Creates confusion, maybe opens doors for gaming the system. Layer 2, data operations. T17, semantic drift and expense policy embeddings. The company changes its policy, but the vector database isn't updated properly. The RI system retrieves outdated info.
Leading to wrong decisions.
Right. Incorrect approvals or rejections based on old rules. Also in Layer 2, T18, RA input manipulation, an attacker crafts an expense report specifically to trick the RA system into pulling irrelevant or misleading policy snippets, effectively bypassing the checks. Layer 3, agent framework. T19, unintended workflow execution, if an attacker can manipulate the agent's internal state. T20 framework vulnerabilities may be a code injection flaw in the RPA software itself. And T21, inconsistent workflow state where the agent gets stuck or acts weirdly due to errors or bad input.
Okay.
Layer 4, deployment infrastructure. T22, service account exposure. The credentials the RPA agent uses to talk to other systems could be compromised. Big risk.
Definitely.
Layer 5, evaluation and observability. T23, selective log manipulation. Attackers altering logs just enough to hide their specific malicious actions, but maybe not erasing everything.
Harder to spot.
Layer 6, security and compliance. T24, dynamic policy enforcement failures. If policies change frequently, ensuring the agent always applies the absolute latest version correctly can be tricky.
Right.
And layer 7, agent ecosystem. T25, workflow disruption via dependency exploitation. An attacker targets a system the RPA agent relies on, like the payment system, causing the whole expense process to fail.
Attacking its support system.
Exactly.
Those extended threats really do highlight more subtle interconnected vulnerabilities. Can you walk us through a concrete example of one of these, maybe that semantic drift one?
Sure. Let's take T17, semantic drift. Imagine the company updates its travel policy. No more business class flights for domestic travel, only economy.
Okay, common policy change.
Right. But maybe the team managing the vector database for the RG system misses updating that specific embedding, or there's a delay. An employee then submits an expense claim for a domestic business class flight. The RPA agent queries the RG system. The RG system, using the outdated embeddings, retrieves the old policy documents that did allow it. So the agent, trusting the RH output, incorrectly approves the expense based on stale information. The company loses money, not because of a direct hack, but because the agent's knowledge base wasn't current.
That makes perfect sense. It really shows how a data management slip-up becomes a security issue for the agent. Now, the guide also gets into cross-layer threat modeling for this RPA agent.
Yeah.
What kind of interconnected vulnerabilities did they find there?
Yeah, they detailed 5 key cross-layer scenarios. First was hallucination-driven data corruption. The LLM in Layer 1 hallucinates a non-existent expense policy rule. The RG system in Layer 2 retrieves this fake rule as if it's real. The agent framework in Layer 3 acts on this bad info, leading to a wrong payment. Spans Layers 1, 2, and 3.
Wow.
Second, privilege escalation. A vulnerability in the agent framework, Layer 3, lets an attacker gain deeper access into the deployment infrastructure, Layer 4, potentially compromising service accounts, Layer 4 aspect, and making fraudulent payments, crossing back to Layer 3 actions.
Okay.
Third, misinformation propagation. Poisoned data in the knowledge base, Layer 2, causes the RPA agent, Layer 3, to make wrong decisions. This bad info might then get logged, Layer 5, or even passed to other systems or agents in the ecosystem, Layer 7.
Spreading the error.
Exactly. Fourth, selective log manipulation and evasion. An attacker uses log manipulation, Layer 5, to hide their tracks after exploiting a weakness in policy enforcement, Layer 6, bypassing audit controls.
Combining stealth and exploitation.
Right. And fifth, agent denial of service. A compromised external agent in the ecosystem, Layer 7, floods the RPA agent, Layer 3, with invalid requests, overwhelming its processing on the deployment infrastructure, Layer 4, and stopping legitimate claims.
Using one layer to attack another.
That's the essence of cross-layer threats.
It's striking how weaknesses combine like that. And the guide mentioned a 6th cross-layer threat for RPA too, right?
Yes. They also added T14, tool hijacking, and parameter pollution. This is where an attacker uses prompt injection, affecting Layer 1, Layer 3 interaction, to trick the RPA agent, Layer 3, into misusing an authorized tool, often interacting with Layer 7 systems, or injecting malicious parameters into legitimate tool calls, could lead to data exfiltration, unauthorized transfers, etc.
Okay, that's a really thorough look at just one type of agent. Let's move to the second use case. ELIZA OS. What is that, and how does MAESTRO apply there?
So ELIZA OS is described as an open-source OS operating system built specifically for AI agents with a focus on the Web3 space.
Okay, AI agents meet blockchain.
Pretty much. It's built in TypeScript. The goal is a flexible, unified platform for creating and deploying autonomous agents that can interact across different platforms, Discord, Twitter, blockchains, while keeping consistent personalities or characters.
Interesting.
It's designed to be model agnostic, so you can plug in different foundation models, and it has this character system to define and manage how the agents behave.
Sounds complex, especially with Web3 involved.
Yeah.
How does the MAESTRO mapping look for ELIZA OS?
Okay, Layer 1, foundation models. This is about ELIZA OS's ability to integrate with various LLMs.
Right, flexibility.
Layer 2, data operations, covers its use of arrayed for accessing info, especially Web3 data like smart contract details or blockchain state handling various data types.
Web3 data handling.
Layer 3, agent framework. This is ELISA OS itself, its architecture, its plugin system, how agents within the OS communicate.
The core OS.
Layer 4, deployment infrastructure. It supports running on different platforms, might integrate with GPU marketplaces, and crucially, interacts with blockchains like Solana.
The Web3 connection point.
Layer 5, evaluation and observability. They mention using proof of sampling, POSP, for verifiable inference, proving an agent actually did the computation plus general logging.
Verifiability.
Layer 6, security and compliance, highlights built-in security features in ELISA OS using blockchain for verification, potential audits, secure key management for wallets,
Web3 security aspects,
and Layer 7, agent ecosystem. Its ability to interact, cross-chain, community management features, analyzing blockchain data, triggering actions on Web3 platforms.
Its place in the Web3 world.
Exactly.
So given that architecture, what specific threats does Maestro help us see for ELISA OS at each layer? This should be interesting with the blockchain angle.
Definitely. Okay, Layer 1, foundation models. Risks like T11, cascading hallucinations if agents rely on each other's flawed outputs. T7, memory poisoning of the underlying models. T26, model instability leading to inconsistent blockchain interactions. This is new, where model non-determinism causes unpredictable on-chain actions.
The model's fuzziness affects the blockchain.
Right. And T1, evasion unexpected output, potentially leading to vulnerabilities.
Okay, Layer 2.
Layer 2, data operations. T17, semantic drift, but now with blockchain data embeddings. T18, R-age input manipulation. T27, vector database poisoning with malicious smart contract data, tricking agents into interacting with bad contracts via poisoned RG data. T12, agent communication poisoning via RG. T28, RG data exfiltration, leaking sensitive data may be related to wallets or strategy.
Poisoning with bad contracts, it's nasty. Layer 3.
Layer 3, agent frameworks. T2, tool misuse. T20, framework vulnerabilities in ELISA OS code. T29, plugin vulnerability, a bad plugin compromises an agent. T30, insecure inter-agent communication protocol within ELISA OS. T19, unintended workflow execution. T31, insufficient isolation between agents sharing the OS. And T32, runaway agent on Solana, an agent bug causing excessive costly transactions.
Runaway agent spending crypto. Okay. Layer 4.
Layer 4, deployment infrastructure. T3, privilege compromise on the host system. T21, inconsistent state, maybe due to network issues. T33, blockchain reorganization attack, indirect. If the underlying blockchain forks, it could mess up the agent's view of reality. T4, network attacks. T34, wallet key compromise. Huge risk for any Web3 app.
Wallet keys always critical. Layer 5.
Layer 5, evaluation and observability. T8, repudiation. T22, selective log manipulation. And T35, manipulation of proof of sampling, POSP, faking the proof that an agent performed a task correctly.
Faking proof. Okay, Layer 6.
Layer 6, security and compliance. T3, privilege compromise again. And T36, smart contract vulnerability leading to agent impersonation, exploiting a contract flaw to make an agent appear as someone else on chain.
Impersonation via smart contracts.
Layer 7.
Layer 7, T13, rogue agents. T12, agent communication poisoning on cross-chain channels. T37, cross-chain bridge attack, indirect problems with bridges ELISA OS agents use could impact them. And T38, emergent collusion on blockchain, multiple malicious ELISA OS agents coordinating harmful actions on chain.
Colluding on the blockchain itself. Wow. That's a really complex threat landscape.
Yep.
Can you highlight maybe one or two of those blockchain-specific ones again? Like the model instability one?
T26, model instability leading to inconsistent blockchain interactions. Think about an ELISA OS agent meant to execute trades on a decentralized exchange on Solana.
Okay.
Because the LLM might produce slightly different outputs, even with similar inputs, sometimes the agent might generate a perfectly valid transaction. Other times, a tiny variation might cause it to generate a malformed transaction that fails, or maybe even one that does something slightly different than intended. That inconsistency is a vulnerability.
Right. Unpredictable results on something that needs precision. What about the runaway agent?
T32, runaway agent on Solana. Imagine a bug in an agent's logic, maybe in its trading strategy, or how it interacts with a specific smart contract. It gets stuck in a loop, constantly trying to submit transactions to Solana. Even if the transactions themselves aren't strictly malicious, each one costs gas fees. The agent could just burn through its entire SOL balance rapidly, effectively a denial of service on its own funds.
Ouch. Accidental self-destruction via blockchain fees. These examples really hit home the unique risks when AI meets Web3. Okay, let's move to our third and final use case. Threat modeling the Anthropic MCP protocol using MAESTRO. What's MCP all about?
So MCP stands for Model Context Protocol. It's an open standard that Anthropic developed. The goal is to give AI assistants a standardized way to connect to external stuff, data sources, tools, APIs.
Okay, a common language for AI to talk to the outside world.
Exactly. It uses a client-server model. The AI application runs an MCP client, and it connects to various MCP servers. Each server basically wraps a specific data source or tool, exposing it in a consistent way.
So developers don't have to build custom integrations for every little thing.
That's the idea, a universal interface to make AI interactions with external resources easier and more standardized.
Makes sense. What are the core components in this MCP system?
You've got the AI application itself, which hosts the client. The MCP client handles the communication. The MCP servers, which are usually lightweight programs exposing specific capabilities. The data sources and tools the servers connect to. Resources, which are the specific bits of data being shared. And often prompts used as templates to guide the AI's interaction.
And the flow is basically user input, AI device, MCP client, MCP server, tool data server, client AI, user output.
Pretty much, yeah. The client asks the server to do something, the server does it, sends the result back, and the AI integrates it.
Now, before even applying MAESTRO, the guide mentions some initial high-level threats they saw just from looking at this flow. What were those first thoughts?
Their initial look flagged the MCP servers as obvious critical points. If a server is compromised, that's bad news.
That's for point of failure.
Right. Also, the security of the communication between clients and servers needs encryption, authentication. The security of the AI application hosting the client is important too, protecting the underlying data resources.
Potential for interference if multiple clients use the same server without good isolation, and the risks if you just expose MCP servers directly to the internet. Basic network security hygiene.
Got it. Standard concerns for any client-server setup. Now, how does the MAESTRO mapping look for MCP?
Okay, layer 1, foundation models. MCP is model agnostic, so this layer is about how any model interacts via the protocol.
Interface layer.
Layer 2, data operations. Relates to the resources MCP exposes. Often implies some kind of retrieval, maybe RA-like, happening behind the server.
Data access abstraction.
Layer 3, agent frameworks. This is really central for MCP. It includes the protocol spec itself, the client-server software, the communication flow, JSON usage, how tools and prompts are defined and used.
The protocol's mechanics.
Layer 4, deployment infrastructure. Focuses on the MCP server, how it's deployed, its use of HTTP, JSON RPC, server-send events, SSE. Notes that initial use might be local.
Server hosting.
Layer 5, evaluation and observability. Just notes the general need for logging and monitoring of both clients and servers, watching the traffic.
Layer 6, security and compliance. Emphasizes MCP's design principles around controlled access, permissions managed by the server, maybe human-in-the-loop approvals for certain actions.
Access control design.
And Layer 7, agent ecosystem. Positions MCP as an enabler for a broader ecosystem, standardizing tool use and data access for many different AI models and apps.
The standardization aspect.
Right. The key takeaway from the mapping is that Layer 3, the protocol itself, is central, but it impacts or relies on all the other layers.
Okay. So with that layered view, what specific vulnerabilities does MAESTRO help identify for MCP?
All right, digging in with MAESTRO. Layer 1, foundation models. T11, cascading hallucinations. If a model gets bad data via MCP. T1, evasion unexpected output, maybe triggering weird MCP requests. T26, model instability, causing inconsistent requests. T7, memory poisoning of the model using MCP.
Okay, model level risks via the protocol. Layer 2.
Layer 2, data operations. T17, semantic drift in the data behind the MCP server. T18, input manipulation for deceptive retrieval if MCP accesses ORI backend. T12, agent communication poisoning affecting data flow. T28, data exfiltration through the MCP channel.
Risks in the data accessed. Layer 3.
Layer 3, agent frameworks. T2, tool misuse via MCP. T20, framework vulnerabilities in client-server code. T30, insecure communication in MCP implementation if not secured properly. T39, unintended resource consumption via MCP, AI making excessive requests. T40, MCP client impersonation, fake client fooling server. T41, schema mismatch leading to errors. T42, cross-client interference via shared server, plus the risk of integrating with a malicious MCP server.
Lots at the protocol level. Layer 4.
Layer 4, deployment infrastructure. T4, network attacks against the server. T21, inconsistent state. T34, wallet key compromise if used with Web3. T43, network exposure of MCT server, making it a target. Also, general resource overload, DDoS type risks.
Server security. Layer 5.
Layer 5, evaluation and observability. T8, repudiation. T22, selective log manipulation. T44, insufficient logging in MCP server client, making investigation hard.
Blind spots, layer 6.
Layer 6, security and compliance. T3, privilege compromise via vulnerable server. T45, insufficient isolation of MCP server permissions, server having too much access. T46, data residency compliance violation if MCP pulls data across borders improperly.
Policy and permission issues, layer 7.
Layer 7, agent ecosystem. T12, agent communication poisoning in a larger system using MCP. T13, rogue agents exploiting MCP. T47, rogue MCP server in ecosystem. Someone setting up a malicious server pretending to offer a legit service.
Fake servers joining the network. That's a comprehensive list for the protocol, too. Can you give an example of a threat that's particularly relevant to MCP? Maybe that unintended resource consumption one.
Sure, T39, unintended resource consumption via MCP. Imagine an AI agent using MCP to access, say, a computationally expensive analysis tool offered by an MCP server. Due to a flaw in the AI's reasoning, or maybe ambiguous instructions, it starts repeatedly calling this expensive tool through MCP, maybe thousands of times unnecessarily.
Oh.
This isn't a malicious external attack, it's the AI itself, behaving badly through the protocol, potentially overloading the MCP server or the backend tool, racking up costs, causing performance issues for everyone else using that server. It highlights the need for rate limiting and careful AI behavior when using these powerful connections.
That really drives home that it's not just about securing the pipe, but managing what flows through it.
Exactly. And like we mentioned, T47, the rogue MCP server, is another big ecosystem risk. An AI application thinks it's connecting to a legitimate server for, say, stock data.
But it's actually a fake one.
Right. Feeding it manipulated data to influence its decisions, or maybe trying to steal credentials or trick it into running malicious code presented as a tool, need ways to verify server identities.
This has been incredibly insightful. We've really journeyed deep into the security challenges of these multi-agent systems and how Maestro helps us map them out in real applications like RPA, agent OSs like ELIZA OS, and protocols like MCP. What are the crucial takeaways you'd want listeners to really remember from all this?
I think the main thing is this. When we move from single AI systems to multiple interacting agents, we get this significant leap in complexity, and that brings a whole new set of security considerations.
It's not just more of the same.
No, definitely not. Traditional security thinking isn't always enough. Frameworks like Maestro give us a valuable, structured way to identify and analyze these unique threats, looking across all the layers and considering those tricky cross-layer interactions.
And it seems clear that these agentic factors, we talked about the autonomy, the communication, identity, non-determinism, they're really at the heart of many of these new risks, aren't they?
Absolutely. Those characteristics are major contributors to the novel threats we're seeing. We have to take them into account when we design and secure these systems. Doing threat modeling, using frameworks like Maestro, is just going to be essential if we want to build robust, secure, agentic AI applications and the ecosystems they live in.
So for our listeners, as they see more AI collaboration happening in their work or just in the world around them, what should they be keeping in mind about the security of it all?
I'd really urge you to start thinking about the security implications whenever you see AI becoming more interconnected and autonomous. If you're involved in building or even just using these systems, ask questions. How do these agents interact? Where could the weak points be? How would we even detect an attack in such a complex setup, let alone respond? That interconnectedness creates amazing potential, but also significant new challenges.
And if people want to dig even deeper after listening to this, where should they look?
Well, definitely check out the OWASP GenAI security project resources, especially this multi-agentic system threat modeling guide v1.0 we've been discussing. You can also find the MAESTRO framework documentation itself on the Cloud Security Alliance website. And, for a more practical feel, maybe look into the specific projects we talked about, ELIZA LOS, Anthropic MCP, see how they're tackling these issues in their implementations.
Great suggestion. So here's a final thought to leave everyone with. As these AI systems become ever more collaborative, more autonomous, how do we ensure their collective intelligence is actually used for good? How do we protect it from those who might try to exploit this incredibly intricate web of interactions within them?
That's the critical question, isn't it? A lot to think about.
Indeed. Thanks so much for guiding us through this complex landscape today.
My pleasure. It's important stuff.